Okay, if you don't hear me, please let me know. I guess you all can hear well. Okay, so last week we talked about the shapes, right? Shapes of crystals. That means they should be very systematic. Okay, and symmetry is very important for crystals. So depending on each crystal, there can be different symmetries in different orientations, right? We can define axes of symmetries uh, based on the shapes of different crystals, right? So these are all because of the internal arrangement, right? Because of the internal arrangement, you should be able to visualize a crystal as a very uh, symmetric item or substance, and also they should have uh, a definite chemical composition, right? So these are important. When we talk about minerals, minerals are the compounds, actually natural compounds of inorganic origin. They should be naturally formed, and they should have the crystalline form. Okay, natural crystalline form. Now you know the crystal, which has a specific internal arrangement as well as uh, definite composition, symmetry, like that, right? Features. So such compounds can be termed as minerals. So for minerals, they should be natural solids, right? They should be natural solids as a result of forming as a result of geological processes, right? Some geological processes, because geological processes are variable. There are several processes that can cause crystallization or of minerals, right? So crystallization of minerals depend on various factors, which we will talk about in the lesson minerals and optical mineralogy in a separate lesson in your second years. Okay, right. Minerals have very specific, beautiful shapes because of they are crystalline, right? As you know, now the crystals have faces, right? So these are faces. So these crystalline materials have faces, or we call facets, right? So depending on each crystal, you can see a very nicely formed shape. So some crystals are elongated like this. So these are elongated, right? One axis, if you define three axes for the mineral, so that the three axes are going through the crystal, you can find that some minerals are elongated in one direction, right? Uh, and in this case, quartz, for example. So if you take this as one axis and this as the second axis, and there can be another axis on the other direction, right? Because these are three-dimensional. So in that case, for quartz, axis number one is elongated. It's longer than the other two axes, right? But specifically, axis number one and two are equal, right? For quartz. For each mineral, such different features are there, right? Depending on the axis length. We call crystallographic axis or crystal axis. We will talk about this later on, but keep in mind along these, the dimensions of these axes are different from one mineral to another. But there are some similar group of minerals which have similar types of axes. For example, for quartz, I said one crystal is one axis is elongated and the other two are equal, right? And not that is not only for quartz. There are some other minerals also having the same type of uh, features of these dimensions of these axes, right? So in that case, we can classify them into groups, right? So similar, there are several groups of minerals which have similar properties like this, right? So later on we are going to classify these minerals based on their crystal shape and symmetry. And also remember, the crystal symmetry is determined by these dimensions of this crystallographic axis, right? So that is important. So this is the formation of natural facets, right? For different minerals, you can see them macroscopically as well as microscopically, even at very small scale, right? For this is nanometer scale, right? This is from SEM, an image of SEM. SEM means secondary electron image. Okay, so secondary electron microscopy, SEM. So you are viewing here a secondary electron image, right? This is a secondary electron image obtained from secondary electron microscope. Okay? We also have SEM in the geology department on the first floor. Sorry, in the ground floor. When you come to the department, you can see that which is used to magnify and observe the properties at a larger at a higher scale, sometimes 10,000 times greater than the normal object size. For example, in a microscope, you can observe only like 100 times magnification, but in the electron microscope you can go up to even higher than 10,000 times, right? So that's a very good advantage we have for analysis. And also atomic scale you can observe in a electron microscope, right? On the optical microscope, the normal microscope, we use light, but instead of light, in secondary electron microscopy we use electron beams, right? Not only observation but also analysis of chemical analysis is also possible using these ones. We'll talk about these things later. You will learn in detail. Right, the morphology is important when you consider about a crystal, right? Morphology means the appearance, outer shape, how you see that, right? So this morphology is important, and based on that you can identify these crystals and minerals, right? So some electron microscopy images, you can see some crystals, right? So different types of crystals, and you can see here it's a cluster. Actually, it's not a single crystal, right? So you have one crystal here, you have one crystal face here, and another here. Actually, these are called twins, crystal twins. We call them twins. These are also natural forms, right? Nobody has manufactured this one. This is natural. These are twins. So twinned crystals, right? So there are different types of twins possible. This is a kind of an intergrowth like thing, right? So many crystals growing together, several crystals growing together, so that it comes as a intergrowth, right? So these are single crystals. The other ones are single crystals, and you can see clear phases, right? Crystal shapes and facets. You can clearly see. These are also taken from electron microscope, right? There should be somewhere the scale. You can see here some micrometer scale is there. Right. So the birth of crystallography, we discussed that the scientist who first started research and then found out very important findings, right? So some laws, right? The law of constancy of interfacial angles. This is one law, and another one, rational indices, law of rational indices. That's the second one, and you can see here the blocks, elementary blocks. Actually, it's kind of a piling up of elementary blocks, we call them, right? So in this case, you can see different shapes, but you see here they have different phases, right? This may be a cube, right? This may be, no, sorry, this is a rhombus, right? These are rhombus, but still, if you take the axis, the three axes here, although here is a pentagon, but if you want to draw three axes there, right? Uh, uh, inside the crystal, you will see all these three axes are equal, right? That means when you project this axis, each axis in three-dimensional space, they cross cut these faces at same distance, right? If this distance is a, you should be observing the other distance, other axis also cutting its face at the same distance, right? So these are the properties, right? This is a special property. This is called a cubic system. We will learn the systems later. In a cubic system, you can see all these lengths are equal, right? But in the bottom one, you see only one axis is elongated, longer than the other two, right? So these two axes are equal, but other other axis is not equal, right? Like quartz, this is not quartz, this is another crystal. But you can see the similar type of properties, right? But the cubic shape is different. So that means you can categorize this type of crystals into one group, right? And the other type of crystals into another group. Okay, so that's how we do the categorization. Even for this rhombus thing, you can see the same crystal length, same length of crystal axes. So this is an example of garnet. Actually, garnet is it belongs to the cubic system. So you can see here clearly their axes are equal. So these are important properties and observations that you have to make when you are with the crystal model, right? So in the lab we have several models of these crystals made from wood, so that you can see natural shapes, right, of those crystals that occur uh, somewhere in the world. Okay, there are about 3,000 minerals, all are crystalline, right? There are non-crystalline ones also, but there are about 3,000 compounds which are crystalline. Okay, right. So we talked about anisotropy of physical properties. That means that some properties are not equally distributed, right, along the axis, right? So some properties are variable in one way along one axis, but along the other axis, the properties are quite different, right? So this is called anisotropy. The property is called anisotropy. That means it's not equal everywhere. Uh, there are minerals and crystals where the properties are equal, right? So in that case, you can call it isotropic, right? Anisotropy and isotropy. We talked about pyroelectric effect. Pyroelectric effect. This is tourmaline, the crystal tourmaline. So there also you can see one axis is elongated, right? So when you heat the crystal in between two phases, like this, between these two phases, you can observe some electric current passing. That's because of temperature difference, right? So that's called pyroelectric effect, right? And here also you can see it's anisotropic, right? Not equally distributed. Electrical, because electrical charges develop only in certain directions, not in every direction. If they are equally developed in all directions, then you can call it isotropic, but it's not, right? Only along some certain phases, right? The 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 charges are distributed. Okay, and another important discovery is the piezoelectricity, right? The piezoelectricity is a result of the external pressure. External pressure causes some electricity to produce. Okay, some electricity to produce by external external forces that cause some pressure on phases. That is called piezoelectricity. So some minerals like quartz, they are characteristic with this piezoelectric property. So it is again due to anisotropy. So anisotropy is inequivalence of the properties. For example, this is just a kind of a model-like thing. It's not a crystal, but just to understand that, you can see in one direction everything is homogeneous, but on the other direction it's not like that, right? So that is anisotropy. So if everything is equally distributed, then you can consider it as homogeneous and isotropic. Okay, and one important thing here is you can see this repeating unit. You have some repeating units, right? These ones are repeating, and also these ones are repeating, right? So there can be several repeating units in one crystal, right? So for example, you may have, if you take this as a unit, is also repeating, isn't it? Right? So there are several repeating units in a crystal, and we will come to that repeating unit later on. So just keep in mind, this repeating unit is important. This is also a characteristic feature of a crystal, right? That is what you call the systematic internal arrangement. We talked about the internal arrangement, right? So that is because of this repeating units, right? So we'll talk about that later. And another example here, you can see some units are repeating. Some units are repeating there, right? So you can take this as a repeating unit, right? Everywhere you can see a similar distribution like that, right? So here also you have a repeating unit. This like hexagonal like thing, right? So likewise, there are some repeating units which make the material very systematically arranged internally, and defining it within the crystal crystal definition, right? For material to be called a crystal, it has to be systematically arranged internally, right? So this is some examples for that. Right. So again, we talked about the birth of the crystallography is as coincident with the birth of solid state physics, right? So solid state physics, their crystal X-ray diffraction was discovered that indicated some systematic scattering of these X-rays when it passes through a crystal. So for that, the crystal has to be very symmetric, right? If it is asymmetric, then you will see these crystal are scattering in different directions without any homogeneity, right? But here you can see this set of X-rays are very symmetric, right? Even to the up and to the bottom, to the downward direction, they are similarly distributed, right? So that means symmetric distribution you can observe there. Right. So these electromagnetic waves, X-rays, you know, they are electromagnetic waves. That those are systematically scattered means when passing through a crystal, it means the crystal structures are periodic. Okay, the crystal structures are periodic, so that's why you see a similar pattern, right? So these are the spots of X-rays bombarded onto a film. Okay, so this is the pattern. And you can see here again some X-rays, some damages on a material, on a plate caused by X-rays, right? But still you can see they are very systematic, right? Very systematically distributed, very beautifully distributed. Right? So that indicates the crystals are internal arrangement of crystals are very systematic. So the first crystal structures were established by Bragg, the scientists, two Braggs. So this is a very important tool, this X-ray diffraction, for determination and characterization of physical structures of crystals, right? So we do XRD analysis in chemistry also frequently to understand about the internal crystal composition and arrangement by X-ray diffraction method. So there are patterns where we detect the wavelengths of these X-rays, and these wavelengths are very characteristic. For example, for quartz, you have a characteristic number, wave numbers, right? But for another mineral, it might be different. So by comparing these numbers or peaks, you can find them in a form of a chart like this, right? Some peaks you can find in X-ray patterns, right? So this peak is different for one. I mean, it is different from the other one by the composition, right? So these two peaks indicate two minerals, but we know these numbers. We have some data, right? Some catalogs like things. By comparing this number in the x-axis, you can understand what mineral is this, right? Without any other observation, you can do that. You can find it. Right. The first real crystal structures came out as a result of continuous experiments, right? Which were started by Bragg, and then they could establish the internal structure of the crystals. So real shape of some crystals were revealed, right? For example, sodium chloride and these potassium chloride like things. So you can see here all these axes are equal. Three axes, they are equal, right? So that means the sodium chloride also belong into the cubic system, right? So likewise, crystal shapes were first discovered, and they won the Nobel Prize also for this task. If you see diamond, so you see here, diamond is having this shape, but still you can find the crystallographic axis in equal size, right? The lengths are equal. See, okay. But for quartz, it's different. It's the equal axis crystals are called cubic system, right? Cubic system, but another shape, octahedron shape. But quartz is different because we saw it before also. One axis is elongated, but the other two axes are equal, right? So it's called hexagonal system, and because of one axis is elongated, we call it prismatic, right? So shape and form, the way they occur is different from one to another. Okay, so this is how the crystals develop in natural environments, right? So you can see here a diamond, right? And you can see here a cluster of quartz, a group of quartz occurring in one place, right? But these are not twins actually. These are not twins. Single crystals occurring in a group, that is a cluster. Right. So we further discussed about the materials and packing. This is important. Packing. So for crystalline materials, they should have a periodic structure, right? It's a 3D array of periodic structure, right? For example, here you can see similar structure, right? Same shape that is repeating within the crystal. So that is what should be observed for a internal arrangement of a crystal. So if you have such systematic arrangement, you can call it a crystalline material, right? You can call it a crystalline material. Quartz is an example. Si2 is quartz. And this can be metals or ceramics or even polymers, right? So these are 3D arrays of materials uh, packed together, right? They are packed, right? That is what you call the packing, systematic packing. But there are some materials which are not systematically packed, right? So those are called non-crystalline material. For example, you can see here this unit and this unit, they are not similar, right? They are not systematically distributed, right? So in that case, these materials are called non-crystalline material. Even for silica, SiO2, quartz composition, you have non-crystalline materials also, right? For crystalline silica, we call quartz. For crystalline silica, we call quartz. And for non-crystalline silica, we don't call quartz. But there are some material we call chert for crystalline, non-crystalline silica. There is a material called chert, naturally occurring. You can find it in some associated with some rocks. But since it is non-crystalline, you can't call it a mineral or a crystal, right? Although it's a compound, quartz is a mineral because it's crystalline and having a definite composition with internal systematic internal arrangement. But for chert, everything is accomplished, but it does not have a systematic internal structure. So therefore, you can't say it's crystalline. So therefore, chert is not a mineral also. So chert is SiO2, same composition as quartz, but it is non-crystalline, right? So these non-crystalline materials we call frequently amorphous materials, right? Amorphous material. So quartz is a crystal, chert is a amorphous material, right? So these are some important points that you have to keep in mind, whether the material has a periodic arrangement or non-periodic arrangement or packing internally. So in that case, you can decide whether it to be called a mineral or a crystal or non-crystalline or amorphous material, right? So that is very important when you discuss about crystals, right? So these are the crystalline materials. Everywhere you can see the same structure repeating, right? Very systematic. And polycrystalline materials are also there. So there also you can see some groups of systematic materials repeating there. But in an amorphous material, you don't see any orderly arrangement, right? They are not orderly arranged. So that is an important feature. So it's very, very important to distinguish these two, whether they are having a periodic arrangement or near periodic. Why we call near periodic means is in the nature, in natural environments, sometimes you can't expect 100% of this behavior, right? Some distortions are there, so that's why. But at least more than 90% if something is periodically arranged, then you can call it a crystalline material, right? But more than 95% materials are perfectly arranged, right? If they are crystallized in a proper under proper conditions, right? Remember all the conditions, physical conditions we call pressure and temperature conditions are very important for crystallization of these materials. Glass is also a non-crystalline material. Glass is also having SiO2, silica composition, you know, the normal window glass, you have a similar composition to quartz, right? Actually, quartz is used to produce glass, but it's an experimentally or industrially produced material. So it does not have any orderly arrangement, right? Although composition is same. So such silica is called fused. Yes, somebody is asking whether we call non-crystalline SiO2 as chert. Yes, I already mentioned, I think. It's called chert. Chert is also occurring in natural environments, right? So this is chert, amorphous silica. Fused silica is the glass, right? The industrial glass. But natural silica, which is amorphous, is chert. Okay, the same composition, the same way they have formed, right? So that is a natural silica, and there is another natural silica formed in associated with volcanoes that we call obsidian, right? Obsidian, obsidian, obsidian. Maybe you have heard, some of you, right? This is called volcanic glass. That means natural glass produced at volcanoes, right? It's a crystallized SiO2, but the crystal size is way so tiny, so that you can't find any crystal shape there, right? So fine. There are such materials, but they are crystalline, right? Obsidian. Okay, we considered the shape and properties, atomic structure, and diffraction patterns of uh, items are important if they have a systematically definable properties. Then we can call them as crystals, right? So periodicity is very important for crystals, so that you have to consider, right? So in crystallography, in the lecture series, we will be discussing about the patterns and symmetry, right? So these patterns and symmetry are very important, so that's why we defined it in advance. And we will define something called unit cell and also lattice, right? Unit cell and lattice, we will come to those later. And then we will discuss something about point group and space group also, right? So all these are related with the crystals, their properties. So therefore, these patterns, unit cell and point groups, space groups, lattice, symmetry, these terms are very important, right? First, we'll see what is a pattern. Like pattern, you know, right? If you see this image here, shown here, it's a cloth pattern, a design of a clothing material, right? So it has a pattern, right? So that is the simple meaning of a pattern that you know already, right? General idea. So in atomic, in a scientific way, with respect to crystal, you can say a pattern is a regular arrangement or periodic arrangement of a motif. Motif, we'll see what motif in 1D, 2D, or 3D space, that you can call a pattern, right? Motif means a kind of a uh, uh, kind of a, say, framework like thing, right? So you have a motif there, and if you have some systematic pattern there, then you can call it a uh, crystal, right? So this pattern will give you a pattern which should be observed in a crystal, right? For example, in a crystal, you can find this type of a pattern, right? So even for example, this flower, right? This flower is repeating as a unit, right, in this clothing pattern, right? In addition to this flower, you can take this hexagon like thing also as repeating unit, right? Because you can see uh, similarly distributing them, right? You can take either the flower itself or this entire unit as a periodic element there, right? It's called periodic element. Element is not like calcium, potassium, sodium, not that element. It's just an component, right? Element. Okay. So even for a crystal, you have the same type of a pattern that is made up of atoms, single atoms or group of atoms, right? So in the previous example, you saw SiO2, silica. It's not a single element having a pattern. Actually, even if you take single elements like this is oxygen, for example, right? This blue one. And this red one, they are silica, right? This one, the red one is here. That is silica, right? That is also repeating, but here it is anyway SiO2, right? SiO2 is there repeating as a pattern. Actually, when you have one Si, let's take one silicon here, right? It is bonded to, okay, I'll use another color. It's bonded to one oxygen like this here, and another oxygen like here, and another oxygen like here, right? And you have one more oxygen bonded like here. So what is this structure? What kind of a structure you are looking here? If you draw three-dimensionally, sorry, I can't draw on this trackpad, difficult. Right, so if you connect these things, what do you get? What do you get this shape? What do you mean by this shape? Right, you can connect the faces there. So this is called a tetrahedron, right? So this is since silicon is there in the middle, right, as the joining element, we call it silicon tetrahedron, right? So silicon tetrahedron means you have one silicon atom bonded with four oxygens, four oxygen atoms, right? So there are four oxygen. Let's take, yeah, we'll take it like this. Four oxygen atoms are there bonded to one silica. Okay, so what is the valency of oxygen? It's -2, right? You know that it's -2. What's the valency of silica? It's +4, right? It's +4. So what do you think that this gives you? This is -8 and +4. So obviously this SiO tetrahedron, silica tetrahedron, will have a resultant valency of -2, right? Remember that this is not a neutral unit. This is important. This is not a neutral unit. This has a valency, right? So many other cations can join to this structure, right, to neutralize this one and stabilize it, right? When many minerals are formed, we call silicate group. In all silicate group of minerals, you have this silica tetrahedron as a common component. Okay, so this silica tetrahedron is joined with some other cations so that it produce another stable compound, right? So that means they produce another mineral, right? Another compound, that means another mineral, but everything is orderly distributed inside, right? So that's why we have we have uh, this type of an arrangement, right? So a regular or periodic arrangement of a pattern uh, is very important, that makes up a systematic or orderly arranged item that you can call a crystal, right? So patterns and symmetry, and also the symmetry is defined by the systematic arrangement. So therefore, these two go together, right? These two go together because they define the two things together, right? Once you have a pattern, it's anyway uh, symmetrical, right? Symmetrical in the sense maybe in along one directions at least symmetric, or two direction or multiple directions, right? So it depends on each and every mineral that makes different, that is made up of different crystals. Okay, so pattern is that. So you just keep in mind, and you can always remember this one. And for this pattern, I told that the flower can be repeating unit, or otherwise this hexagonal like unit, can also be a uh, repeating unit. So in this case, if you think this is a crystal, you have two repeating units. One is flower, and the other one is the compound, or the combined shape of this hexagon. Which one is small here? Flower is the small repeating unit. So there are small the repeating units has different sizes in terms of atoms combined there, right? So flower maybe we can take as just one atom, right? For example, the hexagon can be at least four atoms, because there are four flowers there inside the hexagon, right? So the smallest unit, repeating unit, the smallest repeating unit is this single flower, right? So this single flower is the smallest repeating unit, which we can define as the unit cell. Okay, so unit cell in a crystal is called the smallest repeating unit inside a crystal. So some crystals has only just one repeating unit, so in that case they have just one unit cell. No, sorry, just the unit cell is the same as the repeating unit, but in some crystals there are several repeating units like you observe here. Okay, so in that case you have to select the smallest one, and that is defined as a unit cell. So this unit cell defines the repeating structure of the crystal. So even this the bigger repeating structure that you observe here as the hexagon is made up of several unit cells, right? So therefore, you don't need to take that as the repeating unit, but you have to take the smallest unit as the repeating unit for a crystal. So that is called a unit cell. So this unit cell combination of unit cells, some combination. For example, here you have combination of many unit cells, maybe 20, 50 or something, right? That makes a lattice. So the crystal lattice is made up of several units of unit cells, several units of unit cells, right? So a repeating unit is a unit, it's the smallest repeating unit is a unit cell, and several unit cells will define a lattice for a crystal, right? So you know about lattice. In chemistry also you have learned about this lattice and some shapes of this lattice. Even tetrahedron is a lattice shape, one of the lattice shapes. So that all depend on the unit cell dimensions and its shape, right? Okay, right. So you have another pattern here, right? So A, B, and C. Which one is a pattern? You have single pattern here, right? That means this unit is repeating in all directions as a single unit. So this is the unit cell in that case, right? What about this one, B? how does it repeat? Whether you have a repetition there. You have one mark here and here a different one, and this is different and this is also different. So you don't see any repetition in this direction, right? So if you see the repetition the other direction, do you? No, you have similar repetition here, but not continuous, right? So it's like amorphous material, right? So this should be a non-crystalline material, right? You can't see any repetition. What about the other one? Here, what kind of a repeating unit? Same, although they are different in one direction, but if you take this whole unit as a repeating unit, then you can agree that this has a repetition, right? So in this case, the unit cell is bigger, isn't it? Right? You can take unit cell like this one because it is repeating, but it's not repeating everywhere, right? So the penetrative repeating is important, right? It should be repeating everywhere in all directions, right? Otherwise, you can't call it a unit cell, right? Here you see it's repeating in all directions, right? In all directions. So therefore, you can take this one as a unit cell, single one. But here you have to take this entire thing as the unit cell, repeating unit. Okay. So those are the patterns, right? Patterns, and this also this material does not make any symmetric arrangement, right? You don't see any symmetricity there. In the first case, sorry, in the second case, B, no symmetric arrangement. Here you can see symmetric behavior, and here also you can find symmetric behavior because, for example, if you cross like this part is symmetric, these two parts are symmetric, right? So therefore, you can have some way or the other some symmetric behavior, but here you don't see, right? So in that case, you can say that B is not a crystal, right? B is non-crystalline or B is amorphous, right? If these are crystals. Okay, so in geology, we have to learn about these patterns. That is very important, right? So these patterns are important, which you can use to have some kind of some definitions actually. So the elements which makes the patterns in crystals, right? So they get together and make a mineral as a natural solid which has a crystalline structure. So if something has a crystalline structure, means it has an orderly arrangement, right? It has an orderly arrangement. Atoms are joining each other in accordance with the pattern. Okay. So I showed you some SiO2 tetrahedron, silica tetrahedron. There I told you that there is a -2 charge always for that particular unit. Okay. So in that case, it has to neutralize the electrical charges with addition of a cation, most of the cases. So here, halite is a mineral. Actually, it is the natural salt. Halite means salt, right? It's a it's a mineral name is halite. Although we call it generally salt in normal conversation or colloquial language, scientifically it's called halite because it's a mineral name is halite. So in the sea you can find rock salt, right? This rock salt means rocks of salts, that means naturally forming sodium chloride crystals, right? Not artificial salt like what we get for cooking, right? Stable salt, that's artificially made salt in evaporation, using evaporation, right? But in the sea, in oceans, you can find rock salt that is natural, right? So that is natural salt. So any mineral which is crystalline, which can be which is definitely crystalline, is characterized by a unique pattern. It can be single pattern or several patterns, right? Unique pattern, but anyway, unique pattern should be there, right? So these are three-dimensional anyway. So that's why we defined three axes, right? Remember, three axes we defined. So that means they are three-dimensional. Although we can't see them through, right? We cannot see them through, but using SCM, we can see them through. So that is the importance of an SCM. Right. So this pattern is three-dimensional. This regular arrangement of atoms in minerals we study as the subject of crystallography, right? So mineralogy is a different subject, crystallography is another subject, right? Crystallography is studying about the building blocks of minerals. Building blocks of minerals. Building blocks of minerals are crystals. Building blocks of crystals are elements, right? Elements combine and make crystals, and crystals make compose minerals. So this regularity is reflected by the symmetry. So if something is symmetrical, that means it has a regular arrangement, right? So this symmetry causes external shapes of these crystals, right? External shapes. So that's why we saw different shapes here, different shapes, right? So that is because of this internal arrangement, right? Internal arrangement. Right. So do you have any questions regarding this content? We just started only, right? We just started only, and we discussed about patterns and the repeating units, the unit cell, the smallest repeating unit. That is what you call the unit cell. Right. Okay. If you have any questions, you can ask me now. No. Right. So for today, we can stop here. I will take tomorrow's lecture as well, so that we will continue from tomorrow. Okay. Right.